Thanks a lot, Ali, for the introduction. And thanks first and foremost to the conference organizers, for the invitation to speak here today. I really appreciate it. It's been a really good and diverse conference, and with a lot to be learned on a number of different fronts. What I want to discuss here in the next few minutes are a couple different examples of some work we've been doing, have done at YASA over the past couple years, trying to apply our systems analytical modeling tools to address policy-relevant questions, particularly related to the questions around energy. So the talk is divided into two parts. They kind of hit on and link back to some of the talks we've heard over the past couple days in terms of risk assessment or the multi-criteria analysis work. I'm not going to get too much into the methodological details here. It's really about the application of these works and the policy-relevant problem of energy. I chose these two examples in particular because they're quite pertinent and relevant right now, given the ongoing political discussions at the international level. The first one of these is, and we've heard about this already, the SDG process. You've heard about this already, and many of you would have known about it otherwise. The SDGs were agreed back in September in New York, 17 of them. They supersede the MDGs. I've circled the SDG number 7, which is about energy, not because it's necessarily the most important from my or anyone's point of view, but this is the area that again, the talk is focused on and where I spend most of my time thinking about. It's also one of the goals which has linkages to a number of the other goals. Number 1 on poverty, number 13 on climate action, the goals related to water and food security and communities and health and so on. I'm going to come back to that in just a few minutes as well in the first part of the talk. The second process, international process that's going on, it seems like it's always going on, but it's right in front of us now at the end of the month and continuing into the first couple weeks of December is COP21, of course, the International Climate Conference in Paris. The goal, when world leaders and international negotiators come together at this meeting, is to finally come up with some legally binding agreement to bring the world's emissions on a downward trajectory, reach the 2-degree target in the long run. We'll see what ends up resulting from this conference. Some people are more optimistic than others, some more pessimistic, but any agreement that comes out is going to have to do something about reining in greenhouse gas emissions from the energy system. Okay, so that's what, in this first part of the talk, what I want to focus on. In particular, thinking about the energy system as a system, as an interconnected network of systems, okay, because this is where we can start to identify some of the synergies and trade-offs between some of the different objectives, as I'll hit on in a moment. And so what do I mean when I say the energy system? All the way starting from the upstream side, energy supply. So this is the coal, oil, gas resources that come out of the ground. It's energy from the sun, from the wind, which is of course by the sun, from the sun originally. It's these different processes and activities like power plants and heating plants and oil refineries that convert these raw energy resources into usable forms like electricity, like gasoline and diesel and jet fuel and so on. And then these resources, or these usable energy forms and the carriers, are transported and spread all around the world so that we can use them in our transport sector to supply mobility demands and to meet end-use service demands in the building sector for lighting and heating and cooking, and to power machines and factories. But what I think doesn't get enough attention is that all of these activities and processes here impact and are themselves impacted by the world's agricultural and economic and geopolitical systems, and then those systems in turn affect the environment, and in particular the global climate, but also air pollution and water pollution and so on. And so at YASA we have an interlinked suite of modeling tools, you could say, that try to represent each of these different processes in each of these different domains. I'm showing, this is how this integrated assessment framework looks from my perspective with my bias as an energy person. So I've got the message, the message model at the center, the systems engineering global energy model with regional detail around the globe and all the trade links of energy that flow around the world and all the technologies and so on. This model is connected to an aggregated macroeconomic model. Outputs from these models go into a simplified climate model. We have links of these models to some harder or softer than others, these links, to global forestry and land use models, to greenhouse gas and air pollution mitigation model, gains. And then what really, I would say, kickstarts the system and gets the engine going are service demands, and as I showed before, in transport, in the building sector, industry sector, and these demands themselves come from projections for income and population going forward, so we rely on work from our demographer colleagues here at YASA, for example. All these models are worked on by a number of different folks across the Institute. And in fact, I just realized this slide here, this schematic is a bit outdated because now we have linkages to global water models as well. This is ongoing work and some of the newest work. So we typically use this interlinked suite of models to develop energy scenarios for the 21st century. Scenarios that try to overcome these different energy challenges that societies face. Here's a list of them. It's certainly not exhaustive. Things like energy poverty, energy security, food security and biodiversity, air pollution, water scarcity, climate change mitigation. I'm only going to focus on 3 of these in today's talk for lack of time, but also lack of expertise in all of those areas. I'm also going to throw in a 4th dimension, which is costs or the affordability of energy services. Obviously, this is important, and if you remember back, SDG number 7 is about affordable and clean energy. So, I mean, we have to keep costs in mind in all these cases, particularly for the poor of the world. All of these goals are these different energy challenges are connected, even though they're often talked about and discussed in different circles and in isolation. So the climate change goal and mitigating climate change, we've often hear, this 2-degree target has become standard in the international policy discussions. Okay, in more recent years, we hear this at the national and subnational levels as well, but this is a global problem and discussed at the global level. Meanwhile, energy security, this is a problem that's often discussed at national levels. You hear presidents and prime ministers talking about the need to reduce their energy import bills, to diversify their energy portfolio. And then air quality and air pollution. This is tends to be more of a local or metropolitan area concern, particularly in these quickly growing and massive cities of the developing world, like Delhi or like Beijing, but also in London and Los Angeles and many other cities. So this is a problem that hasn't gone away. In fact, that you could say that about all of these problems and these challenges. Society in different countries and collectively as a globe, we have made progress on these different fronts in recent years, but there's still a long way to go. Why is that? Because the problems are complex. Modeling solutions to these problems is complex, but this is where the tools of systems analysis can hopefully help to inform the policy dialogue and push things, advance the state of the discussions in some way. And this is what we tried to do in an analysis that we did during or within the context of the global energy assessment. So we use this suite of modeling tools with the message energy model primarily doing the work, and we layered in explicit policies of varying stringency in each of these 3 dimensions. So some more weaker than others, some more stringent than others, and everywhere in between. And we kind of combine these into different policy packages. And if one thinks of these policy packages as inputs into a given scenario, then the outputs are the set of system-wide transformations that take place, in this case in the energy system, that achieve these different policy goals. And so in our case, we developed an ensemble of scenarios, not more than 600, which we thought was a lot at the time, not as many as Rob was talking about, 2-something million, but this model probably takes longer to run. So we have computational constraints, of course, so more than 600 what we call energy, climate, pollution, security futures, and each of these is unique. No 2 of them are alike, so Some of them might push only one of these objectives and ignore the others. Some push all three at the same time, a little, a lot, somewhere in between. So we have these different combinations. The work was done with a global focus, but with regional, so country-level detail as much as possible. And, so the reason that we wanted to cover as broad of a scenario space as possible was so that we could start to get a handle on the synergies and in some cases the trade-offs that are there, but the synergies I'll focus on in this talk. And there are synergies in three different dimensions that result primarily from the direction of mitigating climate change and stringent climate policy on the road to 2 degrees. So in the first case, we're talking about the co-benefits for air pollution and health. Basically means that as we're moving, decarbonizing and increasing energy efficiency efforts, moving away from let's say, coal and natural gas plants, oil-powered vehicles that were, and more towards renewables, things that don't emit air pollutant emissions like black carbon or sulfur dioxide emissions or whatever, we're improving air quality, and this improves health down at the local level as well. In the second case, we're talking about countries that, as they rely more on low-carbon, domestically available energy resources, then they reduce their energy import bills, they diversify their energy portfolios, and so you have synergies here. And then in the third case, we're talking about cost savings and spillovers to the tune of, by our calculations, upwards of $600 billion globally by the year 2030 in reduced pollution control and energy security expenditures. I can say a few more words about this third point on the next slide, and you will have seen this in a different form before. I think it was Naki who presented it on the first day. It's basically our attempt to quantify how much it would cost to achieve globally each of these different energy policy objectives on their own, in isolation. So, for example, on the far left, if all we cared about, if what individual countries cared about, namely those that are the big energy importers, like here in Europe or Japan, and increasingly the countries of the developing world, China and India, how much would it cost for them to improve their energy security to a point that was they deemed acceptable and quite secure, from the perspective, as we defined it, of energy independence. Okay, and by our calculations, we're talking 0.2% of GDP cumulative until 2030, a couple $100 billion a year. It's not small, but it's also not enormous. When you compare it to in the middle, for the middle bar, so if society's goal was simply and only to ensure that all the world's citizens were breathing air that is safe, as deemed safe by the World Health Organization standards for air quality, for fine and particulate matter, that's what we use as a proxy, then we're talking about 0.5% of GDP. And then, in the third case, if the goal was only to mitigate climate change, at least by 2030, we're talking about bending the curve and putting the world on a path to bringing emissions down and transforming the system. Costs are higher, getting closer to 1% of GDP. But if, and this is, I think, the main insight of this particular analysis and this part of the talk, is if there's kind of a more integrated, holistic approach to solving these problems, then you see that this is where the cost synergies and spillovers come and can be identified. Costs are clearly higher in this case, but not as, you see this bar is up a little over 1% or so, a bit more than the cost of mitigating climate change only. You would expect that because we're solving 3 goals at one time, but the costs are not as high as you might expect. It's certainly not a simple sum of the 3 bars to the left. And like I said, that's because of these spillovers that you get, technological spillovers from and across the different dimensions. A good example is switching from, I mentioned before, like coal and gas power plants over to renewables, solar and wind production, hydro production. Then when doing that, you obviate the need for installing end-of-pipe pollution control measures, emission scrubbers on a power plant. And if that's a goal that you also care about, you know, the air quality goal, then there's some savings involved when one does the cost accounting this way, then then that counts as a spillover in the total cost of achieving these two, or the third goal, then it becomes less. So you kind of you kill three birds with one stone, in a way, to use that saying. Now, this work was carried out within the context of the GEA, the Global Energy Assessment, like I mentioned, but more recently, we've seen similar insights coming out of the IPCC's fifth assessment report. Here's a graphic from the summary for policymakers, which shows the co-benefits of climate change mitigation for air quality. It's pointing out black carbon and sulfur dioxide in particular, but all these dots signify, these are scenario results from dozens of computer models, these global systems integrated assessment models, like the model we use here, and so it indicates that this is a robust insight, the climate change mitigation co-benefits for air quality. Similar on the energy security front, in that same panel of, or collection of figures in the summary for policymakers, there was also one about this, drawing on integrated assessment model results, multiple models showing that energy import bills are reduced as a result, and the diversity of the power sector goes up. So two kind of metrics that are often used to define, what is a secure energy system. So with that, let me switch gears a bit and into another part of the talk, describing some other work that we've done here at YASA, a bit more recent work that hits on the risk assessment dimension, you could say, focusing on the mitigation side, and on uncertainties. Because one of the things that we realized in the course of doing the GEA and working on that was the future direction of the energy system and, in general, society's ability to mitigate climate change. It's rife with uncertainty. These uncertainties come in different forms. One, on the side of the geophysical side of the Earth system, the other side, the human side, and on the human side, we're talking about uncertainties related to future technology availability and performance. We're talking about future consumer behavior, lifestyle choices, and politics and institutions. And so what we wanted to do was try to get a better handle on those uncertainties, try to tease out kind of which of these uncertainties matter more than others. And so again, we used our systems analytical modeling tools, this message model that I mentioned, and its connections with the other models. And we developed a large ensemble of scenarios, a different ensemble than the one I showed before. This one a bit bigger. And in this particular case, the way we created a number of different scenarios was to vary assumptions on technology availability, on future energy demand growth, on future climate policy, and on the stringency of that policy, and on the swiftness of political action. How is it immediate? Is it delayed? By how long is it delayed? And so you see here that I'm just showing a subset of scenarios here in this top panel. These are just greenhouse gas emission trajectories between now and the end of the century. The key point about these is that two things to note. Each of these scenarios firstly has a certain, let's say, price, cost, better said, associated with it, which some cost over and above some business as usual baseline scenario with default set of assumptions, some reference case. And that cost can be quantified in terms of a carbon price that's a certain value today and perhaps growing throughout the century. And the second thing that each of these scenarios is that's unique to it is its impact on the global climate system. So every trajectory for greenhouse gas emissions has a unique signature on the climate system. But we have to talk in terms of probabilities here. For example, the probability of reaching a certain temperature target or staying below that target because of these uncertainties that I mentioned on the geophysical side of the Earth system, like how much heat can the oceans absorb, how much carbon can the world's forests and grasslands digest. So we had to treat this in a stochastic manner using our simplified climate model. And here I'm showing an example highlighting with this blue line. You can see up on the top panel this trajectory for greenhouse gas emissions, which is I would say a fairly stringent one, meaning emissions are peaking somewhere over the next few years and then coming down steadily throughout the rest of the century. So a scenario like that, by our model's calculations, would need a carbon price of about $20 today and growing over time to motivate this level of reduction. So by the end of the century, we're talking much higher levels for the carbon price. And then in the bottom panel, you can see that this particular scenario has a certain probability associated with it for staying below each one of these different temperature targets. For the 2-degree target, which is that blue circle on the bottom, 50% probability that this scenario stays below 2 degrees, which at the same time means 50% probability of exceeding it. If you raise that temperature threshold to 2.5 degrees, then it's about an 80% chance of staying below 3 degrees, 90% chance. But you can kind of see how this works. What we did is that so if each scenario that I'm showing, each one of these gray lines, and this blue line being the example, each one of those has a pair of these points associated with it. A probability for staying below a given temperature target. Let's focus on the 2-degree target. And then secondly, a cost associated with a carbon price as we use as the metric. And so what we simply did was we took these pairs of points, we plotted them up on a graph, connected all the dots with a line, and we end up with this kind of S-shaped curve that you see here, which is what we call a cost-risk distribution for mitigating climate change. This is our base case, our default case with the central case assumptions in terms of energy demand growth and technology availability and so on, and this is for staying below the 2-degree target. But the way to read this is quite straightforward. Basically, so on the vertical axis, the probability to stay below 2 degrees is 50%. You come down where the point from where that 50% level meets the curve, and we're talking $20 per ton of carbon. So it's basically that scenario that I showed on the previous slide. That was in blue. If we want to kick this probability up to the 66% level, so 66% chance that we stay below 2 degrees, I chose this level because this is considered likely by the IPCC definitions in their language, then this means going up to a carbon price of about $40 per ton. Okay, so it's a doubling. Now, if we wanted to go further, if we wanted to go up to higher probability levels, well, you can see it gets a bit difficult, no matter how much we're willing to spend on mitigating carbon. There's this asymptote of the curve. It flattens out at about, that's 75% or so, and this has to do with inertia on two fronts. Inertia in the climate system, how much carbon we've already put in the atmosphere, and inertia in the energy system, how quickly we can actually decarbonize. I mean, these exact numbers are, I think, less important than the insights that one gets when kind of varying these base case assumptions, which I'll show you that now. If, for example, now we're coming to these uncertainties in the human dimension on the technology side to start with, if we make different assumptions for the availability of future technologies like carbon capture and storage, this can have an effect on this cost-risk distribution and shift the curve a bit. So if we don't have CCS for coal and gas power plants or for biomass plants that then we could then use to generate negative emissions through that route, if those are off the table, if we can't use those, this shifts the curve down to the right, meaning that it's more expensive to achieve the 2-degree target, in this case, at a certain level of probability. On the flip side, however, if it turns out that we're able to electrify a greater portion of the transport fleet than we think is today possible, then this curve shifts up and to the left, meaning that it's a bit less expensive to hit a certain probability target. We did the same thing on the demand side, so the behavior lifestyle side of the system. Here I'm showing these cost-risk distributions at different levels of future energy demand growth. So the green curve is at intermediate demand, so kind of a continuation of future trends in terms of energy intensity improvements every year. The red curve is a bit less optimistic there, so energy demand growth is much higher. The blue curve is more optimistic, so low energy demand. This assumes more compact urban development, switching from cars to maybe more biking and walking, more telecommuting, a collection of factors. And you can see that the main insight here is that what happens on the demand side of the energy system is perhaps a bigger swing factor for the climate than the success or failure of individual technologies on the supply side. And then finally, the fourth dimension that we looked at had to do with political uncertainties, which we conceptualized as a delay in concerted global action to mitigate climate change. And the main punchline here, which surprised us actually, is that the uncertainties in this dimension trump everything else by quite a lot. Maybe that shouldn't be so surprising, considering the current discourse and the situation. But what you see here is even a delay until the year 2020 in a global climate deal, which is the current plan of the UNFCCC. This brings the curve down a bit, further delays to 2025 to 2030, bring it down even more, and then at that point it becomes quite difficult, if not impossible, to reach the 2-degree target, unless we have some surprises on the technology side or energy demand is low. So that's where I'll leave things, and the final insight that I was going to make was not to recap the various insights I brought up, but just to put forth this idea that these systems analytical tools we have can provide a lens through which complex interlinkages can be explored, because they combine information from the natural and social sciences and engineering and economics and behavior and politics and to address the problems of our time. So thanks a lot.